students will be able to find extrema of a function, find where the function is increasing and decreasing, and we'll be able to graph a function given characteristics of the first and second derivatives and find concavity. For the function, find the following, and we're going to include written justifications. Find the x values where the function has relative extrema and identify if they are minimums or maximums. So let's take the first derivative. We have 6x squared minus x minus 1. Now extrema will happen where the first derivative is equal to 0. Now we can factor this into 3x and 2x, then minus 1 and plus 1. So x is equal to negative 1/3, x is equal to 1/2. Let's put those on a number line. We have negative 1/2, actually negative 1/3, and positive 1/2. Let's pick some test points. We have negative 1 we can try, and we're going to plug that into the first derivative. We get a negative times a negative. That's a positive, and that means the function is increasing. Well, let's not forget everything we've learned about an x to the third. Here's what x to the thirds look like. So the function is going to increase, then decrease, and then increase. But, for some of the functions that we have, we're not going to know that. So let's plug 0 in, and we have positive times a negative. That's a negative. So the function is decreasing. And then if we plug 1 in, we get a positive times a positive, and now the function is increasing. So now we have a local maximum, and that's happening at x equals negative 1/3, and we're going to give a justification for that. And the justification for that is f prime changes from positive to negative, meaning that the function increases and then decreases. And then we have a local minimum, and that's happening at x equals 1/2. And then our justification is f prime changes from negative to positive. Find the intervals on which the function is increasing and decreasing. We've kind of already done that with our number line. So increasing from negative infinity to negative 1/3. And this is increasing from 1/2 to infinity. And we know that, here's our justification, we know that because f prime is greater than 0. And then we have decreasing from negative 1/3 to 1/2. And we know that because f prime is less than 0. Find the x values where there are inflection points. Well, that's where the second derivative is either 0 or undefined. So let's take the second derivative. Here's the first derivative right there. So we have the second derivative is equal to 12x minus 1. And we're going to set that equal to 0. We get 12x minus 1. So x is equal to 1/12. And we can put that on a number line. Here's 1/12. And we're going to pick some points to test. And we can pick 0. When we plug 0 into the second derivative, we get a negative 1. So the second derivative is negative. This function is now concave down here. And then we can pick 1. 12 minus 1 is positive. The function's concave up here. So we have a point of inflection at x equals 1/12. Now the justification for that is that the second derivative, y double prime, changes signs. And we don't care if it's positive to negative or negative to positive. It just has to change signs, and that's it. Find the intervals on which the function is concave up and concave down. So concave up from 1/12 to infinity, and we know that because the second derivative is greater than 0, and down on negative infinity to 1/12, then we know that because the second derivative is less than 0. All right, let's Let's go view, and we'll go the dual page. F is an even function, continuous on -3 to 3, and satisfies the following. We have an x value and an f of x. So we have the point 0, 2. 0, 2. Here's the point 0, 2. We have the point 1, 0, and the point 2, -1. So we have those 3 points. F prime doesn't exist. That means we could have a corner or a cusp there. And same with 2. And at 1, the slope is 0. And we know that the second derivative doesn't exist at 0 and 2 and is 0 at 1 also. And that's somewhat helpful, but even more helpful is this bottom chart. F is positive from 0 to 1. That means F is above the x-axis from 0 to 1. F prime is negative, which means the function is decreasing. And since the second derivative is positive, that means it's decreasing concave up. So decreasing concave up, we'll just make this nice smooth curve, decreasing concave up. I'm going to erase this, but we can decrease concave down also. That's an option, but that's not what the chart tells us. Then this is below the x-axis because F is negative. The function is decreasing because the first derivative is negative, and it's decreasing concave down. So now decreasing concave down. Whoop, I should go like that, decreasing concave down. Let's redo that. I've already hit 0, and now decreasing concave down. That should be nice and smooth. From 2 to 3, negative, which is below the x-axis. Positive, which means increasing. The first derivative is positive. And then the second derivative is negative, which means increasing concave down. So increasing concave down. And it doesn't say that at 3 it's 0. So we'll assume that it's just a little bit lower than 0. Now, if f is an even function, that means this is symmetric over the y-axis. So if we have symmetry, then this should be exactly the same on both sides. And of course, I'm not going to make it look like that, but I'll try as close as get it as close as I can. And so there is the graph from -3 to 3.